For thousands of years, humans have tried to map what lies beneath our feet. We've drilled deep wells, pulled up rock cores, and measured the fault lines we can physically reach. Yet, despite centuries of digging, the deep subterranean world remains largely out of reach. We operate on the surface, separated by miles of solid rock, completely cut off from direct observation. This creates a problem known in the industry as geological uncertainty. When you are forced to map massive, complex structures in total darkness, every calculation carries a heavy reliance on guesswork. Navigating an unseen environment at high pressure naturally introduces massive financial and operational risks. The obvious challenge is finding a way to map something we physically cannot look at. We tend to think of the deep earth as a static, silent monolith, an inert mass of stone waiting to be mapped. But the crust is an active, highly dynamic system. It is constantly broadcasting data. Fluid moves under immense pressure. Tectonic forces create microscopic vibrations and temperature shift. The rocks have never been silent. The issue has always been our human inability to capture and understand the signals they send. OmniPetro was engineered to solve this exact problem. Its core mission is to build a digital sensory system that translates these chaotic physical forces into clear, actionable intelligence. To do this, OmniPetro first had to develop a sense of hearing. It starts with seismic imaging. Massive acoustic shock waves are driven down into the crust. As these energy waves hit different rock layers, they reflect back to the surface. By measuring the microscopic differences in the timing of those returning echoes, engineers can map the precise shapes, boundaries, and depths of hidden formations. The system organizes these millions of acoustic reflections, converting what sounds like raw noise into a massive three-dimensional architectural blueprint of the subsurface. Knowing the shape of a structure is helpful, but it doesn't tell us what is actually inside those rock layers. So the system shifts from the macro level down to the microscopic level using petrophysics. Here, OmniPetro calculates the specific material properties of the stone itself. It measures porosity, permeability, and exactly how saturated the rock is with different fluids. At this resolution, a layer of sandstone becomes a complex, quantifiable dataset that explains exactly how energy and fluids can move through it. OmniPetro takes the macro architecture and the microscopic material data and combines them into highly detailed 3D volumetric models. It then deploys AI neural networks directly onto this static digital replica of the underground. The AI analyzes millions of data points to discover hidden patterns. It calculates complex probabilities, systematically resolving the red areas of uncertainty into green zones of high confidence. This pushes the system beyond simply mapping what currently sits beneath the surface. It allows engineers to accurately predict how the reservoir will behave in the future. A predictive model is highly valuable, but it remains a static simulation until it is connected to live operations. By utilizing digital twins, OmniPetro injects live drilling telemetry and real-time subsurface pressures directly into the predictive model. As extraction begins, the actual flow dynamics of oil, gas, and water are fed back into the system minute by minute. This active data stream wakes the system up. The static architectural grid becomes a living digital twin that mirrors the physical conditions of the reservoir in real time. The final component of this architecture is continuous learning. Every time a well is drilled, an operational target is hit, or a geological anomaly is encountered, fresh physical evidence is captured. That new evidence is instantly fed back into the system, rippling through the archives to update and refine every existing model. OmniPetro is effectively learning directly from the physical environment, relentlessly correcting its own assumptions and perfecting its understanding over time. All of these capabilities converge in a single, integrated environment. Geologists, reservoir engineers, and AI systems now collaborate, analyzing synthesized data streams as they happen. Seismology, petrophysics, predictive modeling, and live digital twins have fully merged into one unified geological intelligence system. This platform serves as a sophisticated translator for the oldest, most complex information network on the planet. We may never physically lay eyes on the absolute depths of the Earth's crust, but with a system like this, we no longer have to. A moment of wonder. For all of human history, the Earth was never silent. We have simply, finally, learned how to listen.